Welcome to the University Utara, Malaysia School of Computing. I am Dr. Ala Jabbar Al-Maliki, and today we are looking at the exact intersection of computer science and the law, the process of digital evidence collection. Look at this split-screen comparison to see why copying files is an investigative failure. On the left, we perform a standard file copy. On the right, in the terminal, watch the metadata. The operating system instantly updates the last access time. That single, routine interaction has contaminated the original data. To capture evidence without tainting it, we create a forensic image. Instead of dragging and dropping visible files, we copy the storage drive bit for bit at the binary level. This captures active files, unallocated space, and even deleted data fragments. A completed forensic image is validated for the courtroom using three specific pillars: integrity, meaning the data is unchanged; authenticity, proving its true origin; and admissibility, showing it passes legal scrutiny. Basic IT skills are built around efficiency and keeping systems running, but routine interactions overwrite logs and alter the digital crime scene. To preserve evidence, you must adopt a strict forensic mindset, where every action is documented, deliberate, and harmless to the original device. This flowchart outlines the critical pre-collection phase. Before you touch a keyboard, you establish your legal authority, such as a search warrant. That document strictly defines your technical scope, telling you exactly what you can look for, which then dictates how you assemble your toolkit. The most critical piece of hardware in that toolkit is the write blocker. Think of it as a pair of digital gloves. It creates a physical one-way street, preventing any data from flowing from your forensic workstation back onto the source drive. Once you arrive on scene, your immediate priority is physical isolation. A connected device is a vulnerable device. You physically unplug Ethernet cables and place mobile devices inside Faraday bags to block incoming Wi-Fi, cellular signals, and remote wipe commands. You could execute a flawless technical extraction, but if you step outside the scope of your warrant, or fail to isolate the device from remote commands, the resulting data will be dismissed by a judge. Once the scene is secure, you face the major decision represented in this matrix. On the left, dead box acquisition, the device is powered off, making the capture safe and verifiable. On the right, live response, the device is running, requiring an immediate extraction of memory that carries a high risk of altering the system. Pause the video and consider this scenario. You find a suspect's laptop powered on, and you know it uses heavy full-disk encryption. Do you pull the power port to preserve the hard drive state, or do you attempt a live extraction? If you pull the plug, you lose the evidence. Volatile memory, or RAM, holds temporary data, including the active decryption keys needed to read the hard drive. Cut the power, and those keys vanish in a fraction of a second, leaving the seized drive completely unreadable. The strict rule of digital forensics is to never alter the original data. But to capture fragile evidence like those decryption keys, you must break that rule carefully, running trusted tools from an external drive and documenting the minimal footprint you leave behind. This diagram illustrates how we mathematically prove our image is an exact replica. We process the drive's data through a cryptographic hashing algorithm, specifically SHA-256. It processes the raw data and outputs a highly sensitive, fixed-length alphanumeric string. To prove integrity in court, the forensic software calculates a hash as the original drive is read, and a second hash from your newly created image file. If the source hash perfectly matches the acquisition hash, you have mathematical proof of a flawless copy. A perfect hash guarantees integrity, but authenticity requires a chain of custody. This timeline tracks the evidence from the moment it is bagged at the scene through physical transfer logs and onto a secure server. A verifiable signature is required at every single point of contact. A mathematically flawless hash value means nothing to a judge if an undocumented gap in the chain of custody creates reasonable doubt about who had access to the device. Different types of media require specific handling protocols. This diagram outlines three common edge cases. For a smartphone, instant isolation in a Faraday bag is mandatory. For a cloud network, you rely entirely on legal preservation letters served to the provider. And for a USB drive, a hardware write blocker must be attached before the acquisition software is ever launched. Regardless of the media type, the overarching rule remains constant. You acquire the original device exactly once, you verify its hashes, and you solely analyze copies of the copy. Digital forensics is an inseparable marriage between computer science and the law. Fail at the technical extraction, and your data is corrupted. Fail at the procedural documentation, and your data is thrown out. You must master both sides to succeed. If this lecture helped clarify the digital evidence collection process, please like and subscribe. Drop a comment below letting the UUM School of Computing know which computer science topic to deconstruct next. Thank you for watching.